The New Quantum Era,
a podcast
by Sebastian Hassinger
and Kevin Roney.
I'm going to begin this episode with a quick apology for leaving you all without an episode for over a month now. As you know, we try to get an episode out every couple of weeks. End of year is always challenging for scheduling because a lot of our guests are in the academic world, exams, finishing up grading things. Those types of events tend to get in the way, and then I tend to get behind on scheduling. But we're picking back up now. We've got a bunch of incredibly fun and interesting things planned for the year, which we'll be sharing more about as the year progresses. And today's episode is one that I've been working on for quite a while now. I've been wanting to interview our guest today for quite some time. He's a pioneer in the field in the true sense of the word. He's been working for quite some time in quantum computing. His name is Alán Aspuru-Guzik. He was an author of the foundational paper, the Variational Quantum Eigensolver technique. If you haven't heard of it, the Variational Quantum Eigensolver, or VQE, is a technique for combining classical computing with quantum computing to try to come up with approximations, particularly of the ground state of chemical systems. It's really interesting because I thought it was very innovative. The paper came out in 2013. It was the first, along with QAOA, the first two hybrid approaches to try to get some practical results, something useful out of the NISQ devices that have been sort of the typical output of the hardware vendors for the last 10 years, noisy intermediate scale quantum devices. Variational techniques are actually, they're mathematical techniques that are quite familiar, both in mathematics themselves. They were initially for solving partial differential equations and boundary value problems. They've been adopted in machine learning, and they're used in physics before quantum computing as well, just to in quantum mechanics to get those approximate ground state energies and wave functions. So it was very much an off-the-shelf kind of technique, but adapted very cleverly for quantum computing. The reason that that I find it clever is that it takes advantage of the inherent strengths of qubits and the linear algebra that is native to quantum computers, but manages to or attempts to sidestep the limitations of the devices we have today by only running very short circuits on the device before returning the result back to the classical code that then can take another pass at another iteration of the approximation to get closer to your eventual end answer. As I mentioned, the mathematical approach is also familiar to machine learning, and therefore this type of hybrid variational approach is also core to a lot of what is considered quantum machine learning, early research into quantum machine learning. And so the topic today is work that Alán has been carrying out over the last couple of years to update the variational quantum eigensolver technique with sort of more cutting-edge machine learning techniques. Really exciting stuff, and I think you'll enjoy the interview quite a bit. Welcome back to the podcast. I'm here today with yet another very special guest. Super excited to be speaking with him, Alán Aspuru-Guzik from the University of Toronto. He's a professor of chemistry and computer science and really a leading pioneer in the field of quantum computing from way back when. I actually first saw you speak, Alán, at IBM's Think Summit in 2017. When they were announcing the 53 or 54 qubit system was coming out the next year, and you presented on stage your variational quantum eigenvalue solver, which was a really interesting. I mean, since it was my first exposure to quantum, it completely steamrollered my brain. I don't think it even blew my brain. It just completely flattened me. But it was really exciting because it was something potentially practical we could do with near-term noisy quantum devices. And that was 2013. I think that paper came out. So 4 years earlier. And more recently, you've sort of revisited the variational space with an updated kind of approach. So first of all, thank you for joining us. And can you give a little bit of background on the work that led to that first VQE paper?
Absolutely. So I will start even earlier. So the VQE work is around 2013, 2014. Well, let me start in 2004. So many of the listeners on this podcast were not born then. But just to give you like a 1 minute and a half introduction, when I was finishing my PhD, I joined the group of Martin Head-Gordon as a postdoc. There, D-Wave Systems at the time was thinking about gate model quantum computers. And co-founder Jody Rose handed me over 5 papers that he found were interesting and funded my advisor to think about quantum computing for chemistry. Me, as a postdoc, said, oh, this is really cool, and collaborating with Peter Love and Tony Dutoit and, of course, Martin, we looked at those papers, and I found out kind of an easy mapping to do chemistry on quantum computers. And basically, that paper simulated quantum computation of molecular energies in 2005. Got me, published in Science, got me like a door at Harvard where I started my research group. But the VQE comes from that pressure because at Harvard I said, look, I'm going to do other things that are not quantum computing because quantum computing for chemistry is not a new field. And they said, what are you talking about? We hired you to create a new field. Go and just create the field of quantum computing for chemistry.
No pressure.
Not that others were not working at that, but I said, okay, I mean, I was pretty much one of the first, so we found the first. So I said, bring it on. And I needed to show something by my intermediate tenure promotion. It was around 2010. I need to show something. So I said, you know what? I need to get some results. So I met this fellow, Andrew White, in Australia, a fantastic quantum optician. And we met and we said, like, why don't we try to build a minimalistic phase estimation algorithm for molecules? And we published a paper in Nature Chemistry in 2010 that is the first time, actually, you do a quantum chemistry calculation on a quantum computer with quantum optics. There was a group in China that Jianfeng Du got it like a couple of weeks later after us in the archive, or, like around the same time. I forget if it's before or after, but I'm traumatized by that scoop because we put it together around the same time. And one in NMR, one in quantum optics, and then we just suddenly did that. And it was really cool because we even had error correction. With 2 qubits, you can actually do majority voting error correction. So we got the potential in the surface of the hydrogen molecule. And that's a very interesting paper because I think it's one of the first applied papers in quantum computing ever.
Right.
And what we did in that paper that was really cool, obviously, besides showing error correction and showing that a molecule can work, is showing the most expensive diagonalization of a 2x2 matrix ever done in history. Because really that's what they was doing, right? I mean, like a quantum optics table about this size, just diagonalizing a matrix. Okay, so it is in that context now I need to get tenure that VQE is born. Right. Okay, so don't underestimate the precious academia.
I was going to say, so everybody complains about it, but it sounds like it was a great motivator for your productivity.
I mean, my group was blessed at Harvard. I had like this, like, it's almost like, my group was Toronto also. I have like the rockstars of the field come as postdocs. They want to work with me. So I'm very happy to have some of the best people. And then in this particular case, my team and I were focused on a lot of NMR, and actually we did even NV Center experiments, and we collaborate with a bunch of people doing small experiments of quantum simulation. And there's a moment where like we were thinking about why is phase estimation really measuring the energy in such a complicated way? Why don't we just measure the energy directly? So I went to Gerald McLean and to Manholm Jung, and I told them, like, why don't we measure the energy directly for a Hamiltonian? And then the next day, Gerald came to my office with Manholm and said, we figured out how to do it. This is how you do it. You just write a Hamiltonian, map it into spins, and you measure it. And I said, let's write a paper. But at the time, it was very hard to get a very high-profile paper if it's only theory.
Right.
So I said, let's work with Jeremy O'Brien to do because he was a great guy I met. Very energetic professor about my same age from Bristol at the time, and he's a guy now. He's the CEO of PsiQuantum. He's
right.
They're in a black hole somewhere in the Bay Area building a quantum computer.
Yeah.
I haven't talked to him since then. Maybe one couple Zooms because they are so secretive. Although they have hired some of my former group members there.
I'm sure they have.
But anyway, the whole story is that now there's PsiQuantum doing its thing. But back then, the beginning of PsiQuantum also, right, was this thing. Like it was the beginning of my former company, Zapata Computing, the beginning of PsiQuantum. So many things was the idea of, okay, let's just measure directly and then variationally optimize. Let's actually do what people do in quantum chemistry.
Right.
And that's how VQE was born. It was together with QAOA, which was presented at the same conference in Aspen.
Right.
Eddie Farhi stands up and presents QAOA. Then I stand up and present VQE. We were like, dude, this is the same thing almost. That was the beginning of the variational algorithms family.
Right. Well, and I was going to mention QAOA because at least my impression back in 2017 was that VQE was, sort of the most popular kind of path to take for trying to make progress in chemistry applications in quantum computing. And QAOA sort of led directly into the broader topic of quantum machine learning. Would you say that's sort of accurate?
Yes, quantum optimization in general, of course, quantum machine learning. Yeah. At the same time, my former student, also Patrick Raventrost, was already working as a postdoc with Seth Lloyd. And together they were rocking in a bunch of ideas about quantum machine learning. So I think quantum machine learning, many other people worked on it besides Seth Lloyd. But around my closer circle, I think the person that I recall around the same time really thinking heavily about machine learning was Seth and Patrick. And they were rocking at that as well. So Peter Wittek, the late Peter Wittek, also wrote a textbook on quantum machine learning.
That's right.
So there were other types of algorithms, but obviously later people did variational quantum classifier. We were very, very early on, did the first autoencoder, the variational quantum autoencoder. So the quantum autoencoder was a really cool thing because I was doing the first autoencoder for molecular design, one of my most cited papers. And we were like, oh my God, maybe we can do a quantum autoencoder. And then with Johnny Olson and many other people in my group, Jonathan Romero, we published the quantum autoencoder, which is also one of the seminal papers in quantum machine learning. So that's our contribution. Our contributions. We also worked a lot in the quantum CAD. So that's kind of the era, right? So that's kind of what I can tell you about the VQE. I guess you want to talk more about the GQE, but now people saw a history.
That's where I was getting to. Yes.
Yeah, people saw a history between 2004. Now we jumped into 2012, 13, 14. The thinking then around then. I guess the quantum autoencoder paper came out around 2016, if I remember. So those were the kinds of things I was thinking around that time. And then I guess we can talk about what we're thinking now.
Well, that's where I wanted to get to after this sort of, like you said, the historical context is super important. But I think January of 2024, you published a new paper, which was the Generative Quantum Eigensolver and its Applications, I think is the title.
Yes.
I think it's been somewhat flying under the radar to my way of thinking, because I think it's a really powerful sort of revisiting of those foundational ideas behind the VQE paper, but updating it for, based on everything we've learned in the last 10 years or so, and also for the increasing power and powerful techniques that we've been developing around machine learning and accelerated computing with GPUs. So, and obviously, generative AI has become this incredibly huge topic over the last couple of years. Speak to me, like, how did you apply sort of generative techniques to the variational foundation of VQE, or is that an accurate depiction, for one thing?
Yes, it's a reasonable depiction, but it didn't come that way.
Okay.
So the story is a little bit after the VQE paper came out. Of course, we wrote a paper called The Theory of the Variational Quantum Eigensolver, still with Jared McLean and many others in my group. That is also very heavily cited. It's kind of cited together with the Variational Eigensolver, then a paper where we had the theory and a bunch of ideas that we have of extensions. Very late, a little bit later, there was a very important paper published by Jared as well, before he joined Google, where Jared independently with his collaborators found this idea of the barren plateaus, the idea that in the long n limit, like the expectation value of the gradient of a variational algorithm will actually be zero, will be flat, right? That just has to do with just the statistics of how you do the quantum measurements, and that means that without like previous knowledge of the problem, initialization, a bunch of tricks, you might get lost in the optimization, and that seemed like the doom of the variational algorithms. Yeah.
And is that related in some way to sort of the local minima problem with annealing? Is it similar in the sense that you sort of, without pre-knowledge of the context of the problem, you may end up thinking that you've arrived at a solution, but it's just a locally minimal energy level?
I think there might be some connection between them. We worked in my group on both, but I think I see them differently in different kind of. There might be manifestations of the rule of no free lunch in some sense, but what I mean is that so like you can't rely on the gradient. You can always do gradient-less optimization, but if you have too many parameters, right? Maybe even there you have issues with the noise of your measurements, and so then a mantra in my group became, and people in my group know how it works. Like in my group, basically, I kind of like to set challenges and then keep barking at my students with a challenge, and then see who rises up to the challenge. And a lot of interesting algorithms have come out of that. So I told them once, like, hey guys, we don't want gradients. So there was an algorithm that I proposed to my group. We call it Quantum Angry Birds. I'm not going to tell you what it is, but if you remember the video game Angry Birds, right? It had to do with initial conditions and quantum dynamics, and we call it Quantum Angry Birds. Can you aim at something by like initial conditions? And we started thinking about algorithms. We never published Quantum Angry Birds, but we started thinking about this type of algorithm.
That seems like a missed opportunity. That's very good marketing, Quantum Angry Birds.
Well, we just couldn't make something work with Quantum Angry Birds.
That's unfortunate.
But I'm releasing the idea. If somebody has an idea about how to make Quantum Angry Birds work, just write to me and we can publish the paper together. But those are the kinds of things. Like I sometimes come down at like a group meeting and I'm like, okay, this is what I'm thinking. Now I have to give credit. I mean, the stuff that happens in my group many times is just the postdocs and the students. They come up with the idea. I help a little bit. It's like we're an anarchist collective, as Peter Love likes to call us, right? So then I kept telling them, like, I want an algorithm without gradients. Like, we need to think about a way of like having a variational algorithm where you don't need the gradients in the quantum computer. I want to calculate the gradients outside of the quantum computer. And then this brilliant scientist, which now works at NVIDIA, spent a couple of years in my group, Kohei Nakagi, has all the credit of taking that idea and coming back to me one day and says, and he's very humble and very smart, and he just comes and, tells me, Alán, like, I found a way of doing this. And he says, like, I'm going to use a generative model to generate the variational trials. And then I'm going to optimize the gradients in that generative model, right? Like, so the gradient is pushed out of the quantum computer into this thing. This thing prepares the quantum states in the quantum computer. And that thing, I will tell you what I call it, that thing, it can be any machine learning model. We used a transformer, but it can be anything that generates generatively. You like GANs? GANs. It can be an autoencoder. You can do an autoencoder. So
interesting.
It's cool because it could be even a quantum autoencoder. So it could be kind of cool to have like those quantum. So there's a bunch of things you could do, but at the moment,
Right.
we use transformers were amazing in GP2D.
Yeah.
There's a few reasons we use transformers, but that's why the paper is called Generative Quantum Eigensolver. It doesn't matter what you do.
Right.
Later in the paper, the application is called GPT-QE because we use the GPT, and I'll get into that in the remainder of the podcast. But at the moment, just think about it as a generative model generates a circuit.
Right.
So the first problem is, how do you optimize that? So we have to have a loss function for the model, and that's what Kohei found out, how to have some sort of Boltzmannian e to the minus beta energy kind of loss, a loss that as you keep optimizing the parameters of the circuit, the ensemble of states that you prepare keeps being lower than energy. So you generate a bunch of states, and then the quantum computer only measures the energy of the states. Now it doesn't need to measure the gradient. But then the quantum circuit, based on that ensemble of energies, feeds its parameters to generate tokens, which in turn will generate lower energies.
So the model itself is trained on prior or on test shots or on prior work from that device, or how do you train the model on so that it will generate the circuits?
Let's get on to that, because that's going to be a big part of what my group is doing. But at the moment, what we do is basically just learn on previous evaluations. The first thing is, like, if you're evaluating the water molecule at a particular geometry, whatever system you're looking at, you could start with random parameters and slowly lower the energy. It converges really quickly, almost like BQE converges. It starts learning what parameters lower the energy. So, but it can start from a cold start. Okay. And what the paper has, and the reason this paper is still a preprint is because we got some reviews that were focused on high performance, large scale. People really wanted to see very large scale results.
Right.
And we told the reviewers, like, come on, guys, like, this is a new algorithm. Like, we don't care too much about running it into a supercomputer and just showing you that it can run larger. So we started like 3 or more GQE papers that are being written. And then Kohei and I just corresponded. We'll revise the preprint very soon and resubmit to another journal. So this paper he's been there in the archive because we started so many collaborations. I think Kohei has about 10 or so going on on the GQE, but the paper is kind of like there. We're going to revise it with all our new knowledge.
Right.
So, but anyway, the point is that that preprint shows that we can do that. We can generate you can even start random, for example, and then slowly the algorithm learns, which is important to know. Now, this uses GPT, pre-trained. That's when things get really interesting. Okay, because we could generate large quantum mechanical models, right? Models that could be pre-trained. And what we know how to do nowadays, at least what we are publishing so far, you could imagine our collaborations extend this in a lot of ways. But what we're doing is, so if I have the same number of electrons at this point, and I have, for example, the same molecule with just different geometries, if we have data on a few geometries, we can always predict the other geometries way faster. So it learns the parameterization of the Hamiltonian. And we have done a lot of work on that. Even our first paper in the autoencoder showed that if you learn across the potential energy surface, you can predict the rest. Our quantum autoencoder paper originally did that. We did it also with a paper with Álvar Cervera Lierta that combines quantum machine learning with autoencoders with variational eigensolver. That shows also that we can do that. It's called the meta variational eigensolver. That's another interesting paper we published along the way called meta VQE. So learning across the potential energy surface has been done before. We did it in meta VQE. We did it in the autoencoder. Now we're doing it here again. It's kind of like, we know it can be done, but what is nice about it is that then you can imagine, this is GPT. GPT can read the entire internet. So in principle, can I generate a big data set of molecules? And then the question is how to learn across molecules. And that's where the work is happening.
Is there any sort of relation to how Google has approached AlphaFold, for example? I mean, they're training that model that DeepMind model on known molecular geometries as a way to sort of shortcut to guesses about other protein folding geometries, right? Is there any relation to that type of work or similarity?
Yeah. It's related to that. We want to use a bunch of known examples, and
Right.
then what GQE will do, then not what all the algorithm can do, is it will be very, very good at generating a quantum state right off the bat with machine learning.
Right.
That can definitely then be run in a quantum computer. And then if people are complaining about the accuracy of the GQE, but by the way, you can just keep running longer and lowers the energy.
Right.
But you could always switch to VQE mode and now get the gradients. But now,
I see.
But now you're in a very good situation because you're so close to the minimum.
Right.
That you're not
starting from a much better ansatz, essentially.
You're starting basically at the right answer.
Yeah.
The ansatz will be kind of like the circuit type, but within that ansatz, you will be very close to the right answer, like almost there.
Interesting.
So you could just, my dream, just talk about the future. Let's talk about right now. I think John Preskill, I think it's called NISQ. I forget, I didn't see his paper very carefully, but he talks about the new era. I love John Preskill. It's kind of like our guru of new eras.
Yeah.
Like he just stands up in a very elegant way as always, and John starts saying, now we enter the so-and-so era.
We bring up Preskill once per Q to B, and he tells us whether we're in a new era or not.
Yes, exactly. Preskill. That's Preskill. I always admire Preskill's elegance. I aspire to be, as elegant as him, but you can tell I wear my Mexican guayaberas. I have a different type of elegance. I am more like a comedian, okay? And he's more of a formal. Anyway, I like him a lot. He also makes many jokes. I like him. Anyway, the point is that he announced a new era. And the question is, okay, we have this era and then we have the error-corrected era. So if we extrapolate to the error-corrected era, eventually, all these algorithms that we also have worked on, but now here I want to say like Dominic Berry and my former student Jared McLean and also Ryan Babush, actually more Ryan Babush than Jared, I think, in that case, have been working very, very hard on this, long-term algorithms. My group also works on that. Recently, we have new work by Mohsen Bagheribab that I want to promote on new ways of doing quantum simulation as well. So we also work on that. My colleague Nathan Weeb. So we're also working in my group a little bit less focused, but also on the long-term vision.
Right.
But I think eventually we want to know my prediction. When you're going to run a quantum computer in the future, you might run. this is a speculation, but you might run a GQE to get started.
Right.
Then a VQE. And then the VQE is the guess for a full Hamiltonian simulation.
Right.
Because you need to have a good overlap with the ground state. So
yeah.
I think all the algorithms that I've worked on in my career and others have worked in their careers will come together in a workflow. That Sebastian, you work with our colleagues at Amazon that might run in AWS, it might run in IBM quantum computer.
Well, and that's
whatever
I think
it runs.
Incredibly good point, Alán, because even predictions about like what's the timeline till large scale fault tolerant quantum computers, that's depending on which CEO you ask, you'll get different answers, but what's certain is that there are small numbers of logical qubits on the immediate horizon, right? And we've heard announcements from Quantinuum, from QEra, from IBM, from others who are all on the verge of starting to ship logical qubits. It'll be tens of logical qubits to begin with, but I wonder if that speaks to exactly what you're saying. It's to get the value out of a dozen, 24, maybe 50 logical qubits. You'll need these really sophisticated sort of hybrid architectures, solution architectures that leverage the power, the best powers of classical computing and the best that we can deliver in quantum computing to get to something that's together. The sum of the parts is more than individually, right? Like that seems to be the direction we're going in.
Well, there's no quantum computers with the classical computers around them. I also have predicted together with Jared, actually, I think Jared came up with the term QPU. I actually loved it when he showed me the draft of the draft of the Variational Quantum Eigensolver paper. Somebody can correct me if I'm wrong, but I think we are the first ones to call a QPU a QPU, obviously we were inspired by the GPUs. My group was also working on GPUs at the time, but QPU. And the reason the VQE is very appropriate to call these things QPUs because they're like the GPU. They depend on the CPUs, and therefore the quantum computer really has to be called a QPU. They will never be independent, and they are going to be connected. They're very connected to like a massive supercomputer, as we know, or the cloud or whatever. So that's kind of going to be the future, I think, for near time, and that's why, I think, regardless of the era that we are on, if we're still in the variational era or the new era that my friend John is pushing, I am a believer that, and some people are not. Sabrina Maniscalco just put out a paper in the archive with a bunch of colleagues about myths and truths about quantum computing, and I paid attention to the one that says we're going to be able to do something before error correction, yes or no, and most people believe no.
Really?
Well, I'm still one of those 20% that say yes. I think you have to be more creative, and that's kind of one of the things I want to show. What can we do with an pre-error correct quantum computer? I'm still very optimistic that with enough quantum lemon, we can do lemonade.
Yeah, and you mentioned the GQE technique could use just about any form of generative model for that front end, for the generative part, right? So are you thinking of potentially with VQE, your group created the Tequila framework, which is a sort of an extensible software framework for VQE experiments. Are you thinking about doing the same thing with GQE?
As a Mexican, yes, I like to work on tequila. Good point. Now,
is it called mezcal?
For former postdoc and now independent faculty member Jakob Kottmann in Germany. Although he's from Germany, but I have actually. Is he based now in the Netherlands? No, he's Germany. I don't remember. I have to Google it right now. Just to tell you where he is, Jakob Kottmann. You can hear my keyboard here. In Augsburg, in the University of Augsburg. So he's in Germany. Okay. So anyway, Jakob, which is a rock star, he still is maintaining mostly tequila. So tequila, just advertising here in the podcast, is still a maintained package with real new stuff. We don't have the GQE connected to tequila, but obviously it should be a necessity to do that soon. And I think you correctly told me that people have not got on to the GQE yet. I get this from my friend Shaul Mukamel, a very famous theoretical chemist, that told me, Alán, you kind of want to work 10 years ahead of everybody else. 20 years ahead is too much because then people don't know what you did.
Yeah.
But 10 years ahead is kind of what you should do. And, like if you actually look at my publications now in my Google Scholar, the VQA paper keeps keeping up steam. And 10 years ago, it was not that much cited. And I think the GQE will be the same once people realize, and thanks to your podcast, Sebastian, maybe some of your listeners will be like, oh, what is GQE? I didn't see this paper in the archive. Obviously, there's so much stuff coming up, but
links in the show notes, people.
Exactly. You just figured out that you just helped me out to kind of popularize this, and so I am working on it in my lab, in collaborations with Kohei at NVIDIA, and
fantastic
collaborations across companies and across institutes, across academic and national labs, and so it's going to be fun to see what comes out of the GQE era. But yes, as you say, right now the GQE is one paper and a bunch of little mini eggs that are about to hatch.
Right.
So I'm not gonna disclose what we're doing, but
fair enough.
But in the interest of my students and postdocs and co-authors, and
absolutely
respecting their privacy. But I had to say this: you can imagine many extensions of the GQE, because one of the things I want to say is that GQE is not only for the VQE type problem. You can use GQE for variational quantum classifiers.
Oh. Okay.
So you can create all sorts of other variational algorithms with this. So you can do it for machine learning, returning to machine learning. So you can imagine there's a lot of cool things you can do with the GQE type frameworks. So I think GQE will be the perfect marriage between machine learning and quantum computing. And people will not remember quantum computing without any machine learning pre-computation of the circuit. And this paper will be the seed of that. I'm pretty optimistic that it will be my most heavily cited paper 10 years from now. People right now haven't seen it yet, but it's okay. You're always going to be 10 years ahead of the curve.
That's perfect.
That's something I also learned from Seth Lloyd. Seth Lloyd is kind of like that too.
Yeah. It's guru territory.
No, not guru. Yeah. First of all, in Latin America, it would be called shaman, not guru. But,
okay, that's true.
Yeah, shaman.
Fair.
A wrestling shaman. Yeah.
Okay. Well, that's fantastic. I am dying to know what your group is working on, but I will respect the time that your postdocs and students need to work on it. But that means we're going to have you back, or members from your group back, to discuss that work when it does go public. So you're going to have to promise that. So that's fantastic, Alán. I really appreciate your time. This is super interesting. I'm absolutely agree with you that there won't be quantum computing without sort of that pre-processing that'll be machine learning based. I think there's, AI for quantum as a category is going to be an increasingly important topic, an important area for exploration. I think this paper will turn out to be foundational in all of that area. So thank you so much for joining us.
Thank you, Sebastian, and everybody stay tuned about what's coming out. Very good news coming out from our side. And thank you very much, Sebastian. And yeah, we'll stay in touch as always, you and I, okay?
Absolutely.
Okay, that's it for this episode of The New Quantum Era, a podcast by Sebastian Hassinger and Kevin Roney. Our cool theme music was composed and played by Omar Costa Hamido. Production work is done by our wonderful team over at Podfi. If you are at all like us and enjoy this rich, deep, and interesting topic, please subscribe to our podcast on whichever platform you may stream from. And even consider, if you like what you've heard today, reviewing us on iTunes and or mentioning us on your preferred social media platforms. We're just trying to get the word out on this fascinating topic and would really appreciate your help spreading the word and building community. Thank you so much for your time.